Hello and welcome to this video on Ansys discovery for conjugate heat transfer CFD simulation of a battery cold plate. We have our geometry here of a battery module, 12 cells, a cold plate down at the bottom, cold plate, and a liquid coolant path. The first step we'll do is to assign materials. So I'll hide some items like this, the cells, the end plastics, and the cold plate. So now I'll just highlight the shells, go to the simulation tab, select on materials, pick on, we'll pick on the aluminum alloy here. So that sets those shells. And we'll hide and show the end plastics. Select those two, go to materials, we'll pick on other to go find something. And up here, we'll overwrite, start plastic, get us in the neighborhood. And I don't know, maybe we'll find something of polypropylene. Those two are assigned. And we'll hide the ends, show the cold plate. Materials assigned. Try to do the aluminum alloy for that one too. And then the fluid zone, we'll highlight that. Materials, water liquid. Hide that. Then we'll unhide the cells. Select them all. And now we'll pick on other again. And up here, we'll start typing user. So user defined solid. And for now, we'll put a density of 3000. And we'll have to wait on specific heat and thermal conductivity. The next step would be to go from the model to make sure you have the Explore tab going, open, go to the solid thermal, and we'll hide everything but the cells. Select all the cells. This time we want a heat. So this is active heat, and we'll put a value of 60 watts, which is the total heat for all the cells. So there's 5 watts of heat release per cell. Exit out. It's in the list here, and we also have a convection boundary condition that's automatically added. I'll drop down the coefficient down to 5 and set the free stream temperature to 27 C. Next step would be fluid flow. And right now, this would be our flow. So we'll add in display of the fluid path. And we'll select on the inlet. We'll use a mass flow rate. Put 3 grams per second. And an inlet temperature of 23 C. And next will be going to still flow, and we'll do an outlet. We'll use a pressure outlet. Accept. So now we've got the flow inlet and the flow outlet. There's bonded connections between solid materials, and then there's automatic creation of fluid-solid interfaces between fluid and solid zones. We'll check the notifications here. It's talking about thermal conductivity, so we'll go back to the definition of the user-defined solid, right-click edit, and the specific heat is 0, but we want something like 1224, and we'll use a orthotropic conductivity, do it 32 and 32 in the y direction, and 1 in the z direction. Okay, that helps with that. Now notifications, add a flow outlet. I must have, let's see if I edit here, change this from inlet to outlet. So that fixes that. Now we're down to no notifications. In terms of meshing, so there's a global, and I'll turn everything on. So global fidelity, I'll use something like 66 or 66% here. And then I want a local on the fluid path. So I'll hide everything but the fluid zone. Select everything, go on local, and I'll use 0.5 millimeter. Go all. And I think we're ready for simulation. So we'll go back to simulation options, specify a steady state. That doesn't matter. Additional fluid, we'll be using mass flow weighted average for monitors. And in the solving method, the flow rate is pretty low, so we'll stick with laminar. And I guess we're ready to solve. Check here. It's confirming that I'm using laminar instead of turbulent flow. I'll go over here, press on the solve button. And the solve starts. You can see the progress going around, the little white highlight going around the yellow as it's meshing and doing the actual iterations. It's getting close to being done. As everything turned green, it still says it's solving. You already see a contour of temperatures on the external surfaces. Yeah, the legend for the temperature isn't changing much in terms of maximum temperature, and our simulation says it's complete. So now we can look at some post-processing. Obviously, we have the contour plots of temperature for the module. See the influence of the cool temperature of the coolant coming in through the inlet. We can also look at streamlines. So we'll deactivate the contours, activate the streamlines. Maybe we'll hide. Just focus on the coolant path. We can look at the temperature rise. We can look at the total pressure. We can also look at the velocity. That concludes our video. Thank you for watching. Bye-bye.